Hello, everyone. So I'm Alex Blyth. I'm the founder and inventor behind the technology for Blyth BioSciences. I've spent now 20 years in biotechnology, amazingly. And during that time, we all learn certain lessons. And what I'm going to share with you today is a very personal story, but also I think it's one that gives lessons to everybody here. I think in the industry, we spend a lot of time believing certain mantras to always be true. And what's interesting is if you look back over the decades, some of those mantras have stayed, but many of them have come and gone, and for good reason. And what I'd like to address today is the idea that targeted is good. Yeah? So a lot of us work in the industry, and what we do is we develop targeted therapies off the idea that we're going to just affect this and not affect the rest of the body, like a Swiss watch where we just want to change this cog. And in many areas of disease, that's a very good thing. However, when you look at disease areas which by their nature are about mutation, that massively comes into question. And it comes into question very much for cancers, but also for senescent cells and healthy aging, which really are just two sides of the same coin, as I think we've seen from presentations this morning, that cancer and senescence are very tightly linked, or certainly chronic senescence in cells. So Blyth BioSciences is innately curing cancer. We have the world's only neutrophil-based cell therapy platform. I'm just going to take you through what that actually means and how we've been applying it with quite rightly deadly effect in cancer, and how we are now looking for partners to apply it also to senescent cell killing and healthy aging. So Blyth is a pre-clinical stage biotech. We are moving into the clinic at the end of next year. And our platform developed something called a immunomodulatory alpha neutrophil. And you're all thinking, I think there was a sort of bullshit bingo going on earlier on words you can come up with that sound really difficult. I think people will be looking at that and wondering, well, what's that? But actually, each aspect of that is very real. And the reason is that immunomodulatory is actually the key to curing cancer and indeed dealing with senescence. Immunomodulatory means that actually as you get cells that have cancers, you actually not only kill those, but you actually bring the rest of the immune system into the attack. And that is critical for sustained killing of tumors. And if those tumors come back, then the patient not getting cancer again. So there's a lot of thought that's gone behind this, because we're basically creating a whole new space. This is a complete space where we built patents. We've had those patents approved, already a number of them, and more coming through. But essentially, it was a green field that we've created, because before we came along, people didn't really associate the idea of some people being genetically predisposed to cancer, and some people actually not having any family history whatsoever, and having these privileged immune systems that create what we call alpha neutrophils that I'll take you through. And what we've generated is something that can be scalable and cost-effective. I no longer think the challenge in cancer is about can we cure cancer. A number of cancers already being very well dealt with, particularly with blood cancers, but also some of the softer tissue areas as well, with the lymphomas and so forth. But the real question is, can you cure it affordably in a way that the population can actually afford? There's been a lot of information about CAR-Ts. There's been a lot of money spent on CAR-Ts. CAR-Ts are still costing about £250,000 per patient. That is not an affordable cure for cancer. So what we're about is developing an affordable cure, and I'll talk you through that. We've already had very good results in PDX tumoroid models, which I'll take you through. This is actually data I'm going to share, which is first time sharing in conference. where essentially you can see that we can have cell killing, cancer cell killing across multiple solid tumor types, actually including most of the most difficult cancers to currently treat. And my reason for being here is that I'm, as I say, looking for partners on this iMan platform where we can do other things together. And because we're running our next round at the beginning of next year, we've raised 7 million to date, and we're doing a 30 million plus round in the beginning of next year. So, what is the world's first first neutrophil-based cell therapy platform? Well, there's layers to it. So, at the top layer, we have donor selection. What's special about what we do is we know that not all people are created equal, okay? So, as George Orwell put it in Animal Farm, he couldn't have been more right. And what we see is a massive amount of heterogeneity in the population that I'll share with you on the level of killing you see. So we in cancer can see that a certain privileged donor who has no family history of cancer typically will have 20 times the cancer killing that a patient might have. And we can then give those patients that 20 times cancer killing ability. So donor selection is critical. What we then do is we do gene engineering enhancements potentially to those in our second generation products. We have expansion via iPSCs. I don't know if you're all familiar with iPSCs, but essentially normal stem cells have a limit to how much you can multiply them up and expand them. iPSCs don't necessarily have those limits. So you can bring down the cost of the therapy further to something that could be, sub 50,000 euros. Then you differentiate the cells from the stem cells you have down into the kind of cell you're trying to get to, and then you have the delivery mechanism. And what this means is we have a unique, flexible platform that we can actually apply to lots of different areas. So we've been applying it to cancer, and that's what we're focused on in solid tumors. But we also have patents in things like bacterial killing. We can kill MRSA within, we can kill 80 to 90% of that within just a few hours. Autoimmune diseases, neutrophils can be used to calm the immune system as well as escalate it. And obviously for this audience, senescent cell killing. And that's what I'll come back to later on. My own journey in this is that although I've worked in cancer cell therapies for a long time, I'd always believed that targeted was good, as I said earlier. And what I discovered is, with my own mother dying of pancreatic cancer, and it's a picture with my daughter here, and so she didn't get to see my daughter grow up, which was heartbreaking to me, I realized that the reason targeted therapies will fail in cancer is because tumors adapt and they don't. And essentially, our neutrophil-based therapy is non-antigen specific. So that means it will kill any of those tumor types, irrespective of location of the tumor, or indeed if it's mutated or adapted. And that's what we are about. I'm fortunate to have a fantastic team behind me, and I think it's all very well having a vision, but unless you have incredible executors, that vision's hard to realize. So actually, Oksana Polyakova will be here tomorrow on one of the fireside chats. She's my chief scientific officer, who has been absolutely amazing. And she basically leads our scientific team. So please come to her chat tomorrow. And then we have some very strong advisors who are involved in running our clinical trial that we're setting up from Imperial and King's College. We have a very effective board. And I particularly wanted to draw attention to, of course, Patrick Burgermeister, who was just on stage. Patrick is a great friend and investor. And for any of you who do not know him, and you're an entrepreneur and you've got something fantastic, he's the man you should go and talk to. He's a very calm, measured board member. He gets what you're doing, and he will help you get there. And that's very rare. So he's really fantastic, from Kazoo, who, of course, are tied to the setup of this whole summit. So here's Patrick over here. So I think a round of applause for Patrick, please, because he's been fantastic to us. So the premise behind what we do, what you'll see on the right here is a graph. This graph is showing the killing of two different types of cancer cell. We have pancreatic cancer cells in yellow, and we have lung cancers in green. What you'll notice is on the far right-hand side, you are getting donors who are killing 90% of cancer cells within 24 hours. And then on the far left, you'll see some that are struggling to kill 5%. Okay? I'd like to tell you this is because they're the cancer patients and the rest of us are fine. Unfortunately, that's not true. The people on the far left are walking around thinking they're healthy. Yeah? But the problem is, when you then look at the cancer patients, it's really low. And this could be an indicator of a likelihood that you cannot contain tumors, because this is your immune system is the third layer of defense. So after you started to have a mutation and develop a oncogene, your suppressor gene has misfired and is no longer able to suppress it. It's no longer about the cell. It's about the immune system in the body protecting the body against those cells. And that's where your innate immune system should kick in. The people on the right are the kind of people who will be able to smoke, do what they like in life, and they're going to be just fine. The people on the left are at high risk. Okay? And what we see is this correlates to actually the function we see in the cells. So on the far left, you have cancer patients where it's not just the neutrophils are not killing the cancer, it actually goes the other way into the negative. They start helping the tumor. Yeah, that's how bad this can be, and this is how different neutrophils can be in your body. They can be your worst enemy or your best friend. And what we have at Blyth is your best friend. So Blyth produces something called an alpha neutrophil. We get them from these exceptional donors. So that donor on the far right is called donor 61, and they were in our first research product. And they have these exceptionally good cancer killers, which, when you look at them under a microscope, they're like heavily armored tanks, in that they have a lot more firepower for killing cancer cells, as well as infiltrating cancer cells and recruiting the rest of the immune system. So they are born to destroy tumors in your body, and this is what they're doing for these people who have no family history of cancer. Okay? So whereas we're trying to engineer sophisticated targeted solutions, Mother Nature has already gone through millions of years of evolution and has come up with this. Yeah? It's already had lots of experiments, far more experiments than we could ever do, and it works really well. So that's what we're using. So what we find is these cells are different to normal neutrophils. So when we look at them under a microscope, they look like heavily armored tanks with granules, which is like the firepower behind the killing mechanism of degranulation and calcium ion influx. And they basically have a higher amount of granules in a greater mass. But this is also shown when we do proteomic analysis, and we see highly upregulated levels in proteins that basically relate to effector function and cytotoxicity, reactive oxygen species production, which is basically what's fired out by the neutrophils to cells, and also in recruitment and trafficking. So what's wonderful about neutrophils is they are very good at getting anywhere. So they can get through into tumors, they can cross the blood-brain barrier, they can infiltrate anything, but the critical thing is, have you got the right neutrophil? And that's what these neutrophils represent in getting into people's bodies to help deal with these tumors. So the killing mechanism is shown here on the right. It looks rather complicated, I appreciate, but let's break it down to just say the cells are very good at releasing a hydrogen peroxide. They're using calcium ion overload that then basically ruptures the cancer cell membrane and causes it to lyse. And so this correlates with what we've seen with the better cancer killers having more granule content. The solution solves a lot of problems that the industry have had in cell therapies. You'll hear a lot about problems with in allogeneic therapies having enough donors. Well, we find about 3 to 5% of the population have cells that are good enough to be considered alpha, and we pick those based on them being 2 standard deviations above the rest of the population in their killing ability. And we have partnerships with people like Anthony Nolan and some very large US donor pools. So we've got a donor pool of over 1 million there that's been set up. So that would be enough to actually treat pretty much all the solid tumors in certainly the Western world, and we can expand that even further. So the stem cell harvest part of things, it's very easy to extract these cells, so they're not difficult like you might have heard with things like gamma delta T cells, where it's quite difficult to get them out of the tissue. And they're very easy to mass produce, where it's straightforward. Well, we know how to do it, perhaps, is a better way to say it. And we don't have any purification steps, which a lot of the others have. So what we're talking about is something that's highly effective, highly scalable, and something that could be highly affordable. The efficacy side of things, what's most important to us is that these cells are able to proliferate into things once they're there, and that we can reliably mimic the natural killing that one of these donors has. So let me just show you what that looks like. So this is a graph showing cytotoxicity within 24 hours. This is donor 61, and you can see his fresh neutrophils killing in blood in the light purple. And then in the dark purple, you can see what we produce from our bioreactors when we take their stem cells and mass produce those immune cells so that they can go into patients. And the aim being that one donor treats 100 patients, and with iPSCs, that becomes infinite. And you can see that that's faithfully recreated, and that it outperforms other cell types and the standard of care, Abraxane, which I actually worked on with Celgene for pancreatic, which you can see really looks pretty dismal by comparison, sadly. The killing levels that we see, I'm just going to show you across multiple solid tumors. So you can see this is across bladder, rectal, colorectal, gastric. And what you can see is the 100% is the organoid only. So this is a tumoroid, we can otherwise call it, which is where you actually take patients like a biopsy, and you take those tumor fragments and you culture them up into a 3D model. And in this 3D model, we then subject it to our cells. And that's where we see the killing. Now, these models are really overtaking, in efficacy terms, mouse models. They give 80 to 90% predictive power of what happens in the clinic when you look at retrospective studies and what happens in patients, versus a mouse, which is more like 10% accuracy of what would happen in the clinic. So these are very powerful models, and obviously what we're seeing is we can destroy these tumors pretty much across the board. We're currently working towards our first in-human trial that will start at the back end of next year, with first patient dosed in Q1 2024. That will be in our first line therapy, NLIFT, which is from HSCs. We will then be moving to our second line product, our second generation product, iPSCs, that we'll be looking to then put into clinical trials later for 2025 is the aim. So I just wanted to come back to this model I talked about earlier. What I'm interested in this room is, obviously, we're looking to do a round, and we'd be interested in talking to investors, but also I'm interested in partners in senescent cell models, so people who've got in vitro senescent cell killing models that we could put our cells to work on. Because obviously senescent cells do a lot of damage across the body that I think have been talked about here. And what we see is that there are very similar aspects to cancer and senescent cell killing. We see that both of them, you've got the wrong type of neutrophil causing senescence. Wrong type of neutrophil causes cancer. You've got, or doesn't prevent it. You've got senescent cells that recruit neutrophils, yeah? And that's what you see them doing. They're recruiting them. Now, if it's the wrong kind of neutrophil, it'll actually help the senescent cell, just like with the tumors. And we also see co-culture of neutrophils accelerates the rate of telomere shortening if you've got the wrong kind of neutrophil. So, in summary, the wrong kind of neutrophil acts as a driver of senescence and contributes to aging and disease, just like we saw with tumors. And so if neutrophils can drive senescence, surely they can inhibit it. And so I'm interested in partners where we can do for senescence what we're already doing for cancer and interrupt this generation of senescence in the body by using our cell therapy platform. So if you have something that might be interesting for us, we'd be interested to talk to you. Our focus remains cancer, but we're interested in people in this sort of environment to talk about senescence and what we could do there as well. So thank you all very much for your time.
Would you allow a question or two?
Yes,
yeah?
Please.
Okay, so here's one in the first row.
Thank you. So this is Stephen Helliwell at Rejuvenation. Great talk, Alex.
Thank you.
Do you know anything about the genetics of your best donors versus your worst donors? Do you know what's going on or why? And the other question is like a twofer, sorry. if you look at supercentenarian neutrophils, are they at that end of the bell curve?
Yes, two good questions, thank you. So on the genetics, there's basically a huge amount of genes involved. So it's a bit like you asking me, why is Usain Bolt faster than everyone else? We're going to have to look at the length of his legs, we're going to have to look at his personal drive and motivation, his lungs. So it's not just an on-off gene that we could put in other people, for example. There's a number of different genes involved, and we're trying to get to a large enough donor pool that we can actually separate the wheat from the chaff, because there's so many genes involved. So to know absolutely which genes it is, we're not there yet, but we're doing that work. And sorry, the second question.
Whether you look supercentenarian.
Oh yeah. Well, that's funny you should say that. When this went live in the press and we got a lot of press attention, we got all sorts of people writing in. And there were people exactly like that, where they'd lived a long time, they'd had tumours come and go, and they probably did have exceptional immune systems, actually, but we pick people who are 18 to 35 to be donors because they tend to have the strongest immune systems. And so far, the best donor we've ever had just happened to be mixed race, but I think there might be something in that, but we don't know. Yeah.
Okay, go ahead.
Where does the specificity come from for tumors of this heterologous xenoneutrophils?
So, I mean, everyone's very wedded to the adaptive immune system, and I think, even immunologists I talk to, they spent 90% of all their time working on adaptive immunity. So it's always a bit of a mystery when you look at the innate immune system by comparison, which is obviously a much older, more ancient immune system. So there are a number of surprising things involved that I haven't chosen to put in here because they're a bit complicated to get across in this time. But I think an interesting thing is that there is something to do with when you're having a cell that very rapidly is multiplying, it has anaerobic glycolysis, and so it builds up a lot of lactic acid and carbonic acid, and those things create a negative cell charge. The neutrophils are very good at killing things that have a negative cell charge and finding them. So that's bacteria that have a negative cell charge, funguses, viruses. Once they get in the cell, they make it proliferate too fast. Again, it goes to cell negative. So this is definitely a factor that it helps them identify a threat, but it isn't the only thing. Yeah.
Okay, final question.
Thank you. Dariusz Soldacki, Longevity Center. I'm a clinical immunologist, so I have similar question here. Because you showed that second generation, you want to use the chimeric antigen receptor, CAR, in second generation. So this is the possibility to remove any cells and senescent cells. But you know what type of the neutrophiles you have, and 1 and 2 in your alpha neutrophiles?
So which CAR are we going for? Is that what you're asking?
First question is your confirmation that you want to use a CAR in neutrophils for the targeting senescent cells and other, because you showed because
yes.
First is without CAR, so they working without the target, and second generation can be targeted, I understand.
Yeah.
But which type? It's N1 and 2, it's aggressive or stabilizing neurophiles?
Yeah, it's a good question. So essentially, we're looking for using CARs where the first line and first generation therapy isn't as effective as we want it to be. So it's for dealing with, I guess, the problem children. So if we find certain tumor types or certain types of senescent cell are more difficult, we can develop a targeted method to go for them. And what's really important is, unlike a T cell, an alpha beta T cell, when we create a CAR, it appears to be the case that we don't lose the off-target killing as well. So we basically get a win-win. You get the off-target killing still, of being able to kill anything that looks like a threat, but they get activated quicker when they see what is the exact target. So the short answer is, we don't know yet because we haven't tested the first one to see where it doesn't kill and found those things. But there are targets we're looking at that are quite broad, that are quite attractive, like mesothelin and things like this.
Yeah, thank you.
Thank you.
It was very fascinating.